Good morning. So I hope you're all awake. I'm going to be talking about JavaScript today. And I've been asked to introduce myself. I'm Lars Bak. I'm a programmer at Google. The last 23 years I've been implementing virtual machines for object-oriented languages. I've been part of groups that have done 2 Java VMs, 2 Smalltalk VMs, 1 self VM, and now 1 JavaScript engine. So the talk here today is what you see here. I'll talk a little bit about why performance of JavaScript matters. I'll talk about the goals of V8 and how we designed it. And then I'll show you some measurements I did about object heap scalability. And what a big surprise when you use most browsers today, they suck when it comes to object heap scalability. I'll talk about the current performance bottlenecks we have in V8, and then I'll talk to a few points about how we can make it faster and my predictions for how fast we can make JavaScript inside the browser. It's great to be here at Microsoft. I'm from Google, and it's good that at the technical level we can sort of exchange ideas. So let's go right into it. I hope if you have some good questions, you can ask them right away. So, motivation for a new JavaScript engine. So we started this project 2.5 years ago, and it was pathetic when we looked at browsers 2.5 years ago. They were all equally slow. I don't want to mention any ones that were really bad, but they were all slow. Same speed, basically. Not only were they slow, they did not scale when it came to amount of code and amount of objects you had inside the browser. So they would they just degrade very quickly when you ran anything on them. And then you would have memory leaks if you ran the same web app for a long time. And one example is, since I'm from Google, we do Gmail. So if you run Gmail for half a day in some of the old browsers, suddenly you will be spending 200 or more megabytes of memory inside that browser. Not good. So that was certainly a kickstart to doing this VM. And since I've been doing VMs for most of my professional life, the answer is, of course, to build a new one from scratch. And we already decided from the beginning that it has to be an open source project because we wanted all browsers to have a really good JavaScript engine. So we wanted everybody to see how we built V8, and also we want to make it available under a license so that everybody could take it and use it if they wanted to. So the conclusion is here, there's no good excuse for not having a fast JavaScript engine today. Implementing a fast JavaScript engine is not easy. If you look at the language, it's very dynamic. Properties are added and changed and removed on the fly. Objects can be used as a hash map, so it's somewhat strange. And properties in the prototypes can change as well. So if you compare that to a class-based system, it corresponds to stuff in the superclass changes while you execute. You can move functions from the library to an object or the other way around. And array elements, they are not like normal array elements like in Java and C#. They are normal properties in an object. And then, of course, then you have stuff like eval, where you can evaluate a string as source code, and that can change the context of the calling function. So that's good. When we started out, it was clear that most web applications, they were sort of small. And they didn't have any libraries, so we couldn't really use them as a target for building this VM. We wanted to make this VM scalable. We wanted to make it run really fast on well-factored code. So we had these 3 things we wanted to fix. We wanted to have fast property access. We wanted to have fast function calls, so you can implement libraries in JavaScript. And then we wanted a fairly decent garbage collector, a memory allocation system. So here are the core ideas behind V8. It's very simple. We added classes to JavaScript behind the scenes. And then we decided that interpreters were just annoying to have around. So we just converted the source code directly into machine code. So there's only one way of doing execution in our VM. And since we introduced classes, we can then apply classic optimization techniques like inline caching and so forth. And then we implemented a good garbage collector. Here's how we represent objects in V8. And for you guys that wants to run on top of CLR or JVM, this is important, right? Small integers are immediate, so you don't have to do boxing when you do an operation on integers. And I think that's key to get performance in dynamic systems. So yesterday we heard about dynamic languages that are ported to CLR, and I guess you can do the same to a JVM. But the problem is, because you have this underlying system that's based on basic types, you basically have to do boxing whenever you do operations on integers. We didn't do that in our system because we wanted it fast. So small integers are immediate, and objects, object pointers are tagged in a certain way, so the last few bits are 0, 1. So that's the reason why we can distinguish pointers to heap objects compared to what is a small integer. JavaScript objects are represented like this. Here's the object. It has a class pointer. Since we introduced classes, it's not visible at the user level, but behind the scene we have a class. And then we have done a separation between name properties and index properties. And the reason for that is we want to do different optimizations based on if it's a name property or an index property. So that's about it. Very simple, straightforward. And for all of you guys that have done Smalltalk virtual machines out here, this should be motherhood and apple pie. The idea with introducing classes came from the Self project. The Self project is a prototype-based object-oriented language that's like a successor to Smalltalk. And the way they made that fast was introducing maps behind the scenes. So that seemed like an obvious way of also optimizing JavaScript, and that's what we did. And the idea behind maps is that you can share structures between objects. In JavaScript, objects are independent, but often when you run the program, you'll create objects that look the same number of properties and so forth. And the reason why that matters is that if you look at a standard object-oriented language like C# or Java, when you access an instance variable, it's basically you just go to the object, find the nth field, and suck it out. That's how you access an instance variable. In JavaScript, it's somewhat more complicated because you have to treat each object as a hash map. So you basically have to do a lookup each and every time. And that's expensive, and we want to get away from that. So here's a small animation slide that should convince you that these hidden classes is a good thing. So what we have here is a very complicated JavaScript program. It has a function called point, takes x and y as parameters, and then it sets the x and y parameters on this. And here you have two statements that create two different points. So what happens in V8 is that when you say new point, it will say, oh well, now you use this function as a constructor. Then you create one of these hidden classes called class 0. And when you then have created that class, you create the instance P as a point, and we have a backing storage where there's no properties in it right now. When you then execute the first instruction, this.x equals x, you will create a new class. It's called class 1. And in that class, you'll describe you have a property at offset 0. And at offset 0 in the backing storage, you will put in 1, which is the one coming from here. What you also can notice is there's something called a map transition. And that tells you that if you have an object with class 0 and you add a property x to it, please use this transition and find the new class for the object. Likewise, statement 2, when you assign the y property to a point, it finds out it doesn't have it inside the object yet, so you create a new class called class 2. And you can see here you now describe that you have x and y as properties, and you can assign 2 to the backing storage. And then, of course, you have to put in the transition from class 1 to class 2. That looks like a lot of work. Now, unfortunately, what happens is if you create another object, q, you can easily walk through the same statements. All you have to do is change the class pointer of the object and then assign the backing storage, the value. And that's fairly quick. Okay? That's how classes work inside V8 and how we manage to have these transitions also work. All right. Since JavaScript can be used in many strange ways, you can start using it as a hash map. We actually have a policy inside the VM, so if you add too many properties to it, it will say, whoa, then we don't want to handle the object with classes, and we just revert back to a hash map implementation. So we basically have the same performance as any other virtual machine for JavaScript. And that's pretty much it. Now, so by introducing these classes, we actually know if there's shared structures between objects. And now we fall back to standard optimizations in object-oriented virtual machines. We can actually use the same optimization that's being used in Java and C# and Smalltalk for that matter. And one of the classic optimizations is that you can use inline caching. And what we did after we introduced the classes, the hidden classes, we actually ran a bunch of programs and to figure out how many different types or hidden classes you saw at one execution point in the code. And it turns out in 90% of all code points, you only saw one shape of objects. And that tells you can use these inline cache techniques to get fairly good speed. You don't have to sort of put in an inline cache and then change it afterwards. So that's what we did.
Question?
Yes?
When you say, can you back a slide? When you say that JavaScript is not as dynamic, are you saying that it's just not being used as dynamic? I guess it's a question. Is this a question about the JavaScript, or is it a statement about how JavaScript is being used?
It's a statement about how it's being used, right? Because if you look at JavaScript and its specification, it's spaghetti everything, right? You can change anything you want. So if you take that approach, you'll never get a fast virtual machine or a fast engine. What you have to do is you have to look at how programs behave and then design a sweet spot solution for it. So you have to optimize the common case of usage, and that's what we did.
Oh, I think that's a great approach. I just was making sure I understood what you were saying here on this slide, whether you were commenting about JavaScript as a language or common JavaScript in its common usage.
Now, fortunately, what I can tell you, even though it's very dynamic, programmer actually writes well-structured code, even in JavaScript. At least the successful ones. Anyways, so we introduced classes, and we know now we can use inline caching. And you all know what inline caching is, right? No? Whoa. Inline caching is a way at a certain point in the code to capture the receiver type you saw the last time you executed it, so that the next time you get around to that point in the code, you can reuse this information you saw the last time. So in case of loading a property, let's take the point case. If you next time get around to try to load the y property, you just check that the class is a class you saw the last time, and if it is, you know exactly how to fetch the property value out of the object. Okay? So that's inline caching for property load. We also use it for property store and property calls, and it works great. And then if it doesn't work, we fall back to a sort of megamorphic case where we use a lookup cache. But that doesn't happen very often. The inline cache, the code for the inline cache, we generate in small stubs that floats around in the object heap. Okay. So the garbage collector also takes care of removing unused code snippets. And in order to sort of make sure that we run in small amount of memory, whenever we do a full garbage collection in V8, we actually flush all inline cache stubs. That was easy. So I did some experiments. I don't want to talk about if V8 is faster or slower than other ones. It's faster, believe me. But here I want to show how well browsers scale when it comes to object heap size. Okay. So what I did was I took the ray tracer benchmark. It's part of the V8 benchmark suite. It doesn't really matter what benchmark it is as long as it's allocating a lot of objects. And then I made a loop. For each iteration in the loop, I allocated a megabyte of tree structure that I added as a permanent kind of thing in the heap. So what will happen that for each execution of the benchmark, you will have a larger working set in the heap. So I ran this for a number of browsers. There's Chrome, there's Safari, there's Internet Explorer, and Firefox. And as you can see, V8 is up there. It degrades somewhat. Down here you can see that this is how much extra working set we added to that execution. So it's going from 1 megabyte to 20 megabytes of extra data. I can tell you just as a reference point, usually when you run Gmail in a browser, you use 10 to 12 megabytes. So it's not unrealistic sizes when it comes to object heap. But you can see some of the other browsers, they actually degrade fairly quickly as soon as you add objects to the heap. It looks like Internet Explorer, even though it's somewhat slower, it actually doesn't degrade very much. So, but let me show you. I then decided that I wanted to see how much performance degradation we had compared to the first run. And there it doesn't look too good for Internet Explorer either. Even on the previous one, you could see it was basically a flat line, but that was because it was fairly close to zero. So there's a lot of stuff browser implementers should do in order to get this to work. And I think it's a key if we really want to have fast web apps out on available on the web. So here's a concluding slide on that experiment. So you might think that this is a fake experiment I have been doing here, but it turns out it's sort of comparable to have multiple tabs running inside one browser. So if you start up Gmail or another web application and then run the benchmark in another tab, you'll precisely get the degradation you saw in my experiment. Chrome is a little bit special because it actually, for each tab, it creates a new process on the OS. So you can say we're cheating, but it turns out that you can start up in a single process mode and we still scale fairly well when it comes to V8. But again, you can also, when you do a web app, have several iframes, and that is forced to run inside the same process, and you'll get exactly the same problem. So the garbage collector we have implemented in V8 is very, very simple. It's stop the world, which means that when you want to do a GC, you stop the mutator, then you do a garbage collection in a single threaded mode, and we also have a generation-based garbage collector. So straightforward implementation, but that's sufficient to actually get fairly good performance, even though you increase the size of the heap. So here are the different kinds of garbage collection types we have in V8. So we basically have two generations. One is a new generation that's controlled by a copying collector. And usually you get pause times that are 1 to 2 milliseconds on a desktop system. And I would guess that 90 or 95% of all DCs, they are scavengers or copying collections. When objects survive the young generation, they're promoted down to old generation, and there we have two collectors. One is the Mark Sweep collector. It's somewhat slower, 30 to 50 milliseconds, if you have 10 to 15 megabytes of heap. And then we have the Mark Sweep collector, Mark Sweep compact collector. And it's somewhat slower because you have to defragment the heap. The reason why I've done this separation is, of course, that in most cases you can just use this one here, but if you get fragmentation in the heap, you can apply the compact version of it, and you'll make sure there's no sort of unused memory holes in the heap. And in particular for mobile phones, where you don't have too much memory, this is a good thing to have. So if you ever think about implementing a virtual machine for any object-oriented language, do not implement a conservative collector, because that will make it impossible to move objects. Yes?
So the Mark Sweep, excuse me, does the Mark Sweep imply that you can have free space lists in between objects?
Yes.
And you allocate objects into them?
That is true, that while we do a Mark Sweep, the holes we get in the heap will be sort of collected in a free list. And we use the free list when you promote. But at the same time, we keep a score how much fragmentation you have in the heap. And if you go beyond a certain limit, we would do the Mark Sweep compact to make sure that we don't use too much real memory compared to how many objects we have. Code generation is very simple. We translate our source code directly into machine code, thereby skipping the bytecode generation. And the reason for that is that in JavaScript, the primary representation of a program is source code. You can take any function and say to string to it, and you will actually get the source code. So there's no need to have bytecodes. The second one is the core of implementing a virtual machine is making it simple. So just having one mode of execution makes it much more likely that you'll get a robust. Anyways, so our compiler is this very simple compiler that will parse the source code, generate an AST, and from the AST we generate the code directly. It's a one-pass compiler, doesn't do any optimizations. Read. It's good to have a slow compiler because that gives you job security. We made two versions of the backend, one for ARM and one for x86. So it's, I guess, if you want it on a mobile phone, you can use the ARM version. Seems to be the most use for that. Anyways, here's the JavaScript performance compared to ourselves. Over the last half year, we have the original beta, which came out in September last year. We had the final version came out in December, and then the current beta 2.0, came out a few weeks ago. And we have two sets of benchmarks. There's SunSpider benchmarks that's being used a lot by other browser vendors. And we made our own because many of the programs down here are sort of small and we made a benchmark suite that has more than 12,000 lines of code to make sure that we could sort of measure V8 against code that's layered and had abstractions, which is very hard to find in this benchmark suite. I'm fully aware of that it's not a good idea to make your own benchmarks for your own virtual machine. But hey, if you have to go through the spec committee, it takes a year more, and we should do that going forward. But since we also want to get the system out and get it measured, it's good to get it, make your own. So since you're also in the business, at least Microsoft, of doing JavaScript, we'll be more than happy to collaborate on on improving or making a new benchmark suite that will be applicable to and accepted by the whole industry. Anyways, we got a factor of 2 in half a year. That's not too bad.
Does the benchmark suite involve DOM manipulation and rendering, or what
No.
is actually measured?
Rendering has nothing to do with JavaScript, really. So these benchmarks, so here they are pure JavaScript benchmarks. I'm fully aware that you also need something that measures the integration with the DOM, but for V8, it's just pure JavaScript execution.
So when you're saying pure Java, so this isn't doing things like gaming it by having a really fast regex system, which I know some of the JavaScript implementations recently got a big speed boost basically by improving the speed of their regular expression processing as opposed to the JavaScript processing.
It's sort of debatable. We didn't have a fast JavaScript regex implementation in the beginning.
Okay.
We used PCIe. However, regular expressions are used a lot in JavaScript,
Yeah.
so you have to make it fast.
Yeah.
And since we had the backend for generating native code, we decided, well, instead of having all this legacy code of PCIe, we threw that out, and we just generate machine instructions for doing the regular expressions.
Okay.
So we are somewhat fast.
Some of the speed comes from doing that better, but it's in the context of the system. Okay.
You have to make everything fast, right? So if we've done a lot of analysis of how JavaScript is used, and a lot of the web applications, they use regular expressions for doing unpacking of stuff and searching through a lot of strings. So I think you have to make it fast, and yes, we've done that, but V8, that was not, you can take the core engine is independent of the regular expression. Regular expression implementation is sort of an appendix kind of thing on the engine, but it has to be fast too. Mm-hmm. But that's not the reason why we're seeing this factor of 2. Yes?
Do you anticipate some performance problem when you integrate with, when you're measuring the integration between the JavaScript and the rendering?
Well, the numbers of before, that was inside the browser.
Can you repeat the question?
No, I mean,
Okay, so do we expect a performance degradation when we run inside the browser?
So when you are interacting with the DOM.
Well, in this case, you don't get degradation because these benchmarks are not using the DOM, but it's clear that you get a different profile, performance profile, if you have a DOM benchmark, right? The DOM benchmark relies on several things. It relies, of course, on the interface between the JavaScript engine and the DOM nodes, but it also relies on how the DOM nodes are implemented in C++ or C inside your browser, right? Some browsers are using reference counting for doing memory management, and we have to support some form of weak pointer finalization in order to clean up our objects that are bound into the DOM nodes. So yeah, you get a different profile. There's no real good DOM benchmark suite available so far. There are some micro benchmarks, but they are sort of useless in trying to predict how real applications will perform. But I'm interested in if somebody comes with a good benchmark.
I guess the question being asked is how realistic is it to do some pretty computation-intensive ray tracing JavaScript in the context of a browser, when in fact most browser apps end up using it? That's the question that implicitly here is being asked. Because that's...
Oh, ray trace is not very realistic. So, but if you look at the V8 benchmark suite, that's one of the benchmarks. There's other ones. So you can always, if you take small apps that are currently running in browsers, I don't think they're a good prediction how programs will be shaped in the future. We had to get benchmarks that are well factored, that had decent amount of code, so we could target V8 for that. If you just look at the past, you'll never move forward. Here are the current performance bottlenecks in V8. We implement a very slow write barrier. that tracks pointers between old space and new space. Partially to do with we don't use virtual memory for the segments in the old generation. Inline caches resides inside stubs, so you have to do a call whenever you do a property load. That's sort of silly, we can just inline it. So that will get much faster. We don't do any static code analysis in the compiler because it was not necessary to get the good speed. But as performance competition picks up, we'll certainly add value tracking of variables and stuff like that. And then we can see some better optimization inside the compiler. In the current implementation, global objects are treated like any other objects in the system, and that's sort of unfortunate because they're oddballs. So trying to capture the shared state of an oddball is sort of stupid. So we can do much better here. And I did an experiment with one of my colleagues, and on some sort of intensive benchmarks that are using the global object, we can actually get a factor of 2 in V8 on that one.
Question. If you inline the stubs, you wouldn't be able to collect them. Do you think that you would come out ahead?
Yeah, so, well, you can inline in certain cases, right? So if you know that, well, if you do it in a restricted area, you can make sure that the code inside the stub is only a few instructions, so it doesn't cost much more to inline than to have it out of line. But of course, you cannot collect it when it's inlined. But what you do is just rewrite the code, so you sort of lose the knowledge.
Invalidating the cache becomes more difficult, I guess.
No, just iterating over the generated code is not complicated. We do that anyways. You have to do that when you flush the inline cache stub because you have to rewrite them to the initialized stub. All right? My prediction for JavaScript performance is that we'll double the speed within a year when it comes to pure JavaScript performance. And within 3 to 4 years, we should at least get a factor of 4. So, and I don't see any major bottlenecks in doing that other than it's hard work. Yes?
What's your opinion or outlook or plans about this new technology, tracing trees, trace monkey? It looks like they outperform you guys.
Oh, okay. Yeah, I look forward to that. Okay. Should we run the benchmarks? Okay, I'll do that. Do we have time to run a benchmark? So I'll start Chrome. You ready? So let me see.
But I've seen some reports.
Capital A.
Capital A.
Capital A.
-5 lowercase j.
We should be there. So you go to that page, you run the code. So run this benchmark suite. Remember the number. So we have Mozilla Firefox 3.1 beta 3. I believe that includes the trace-based compiler. Let's go and close this one. So here's the run button. You just want to make sure you know that higher scores are better. So that was a factor of 9 with trace-based compilation. I think they'll do better as they go forward. They have not shipped the product yet. I think they'll fix all these. They still have problems with, as far as I can see, with the trace-based compiler falling off the traces. And so in some cases...
Yeah, but what's your look at this technology?
Let me be positive in that I believe that having a very simple execution engine where there's only one mode of execution makes it easier to make it robust and predictable. I have a hard time seeing the predictability in trace-based compilation, but that's my personal opinion. I've done a number of virtual machines. One of them is StrongTalk. It's a Smalltalk system where we actually did a lot of advanced compilation strategies where you had an interpreter where you collected type information as you executed the bytecodes. And then you had actually two kinds of compilers to generate more optimized code. But when you collect when you base a compilation based on the source code plus type information you collected while running the program, right, you get into situations where it's more complicated to get it robust. So we decided when building this system that it was paramount that it had to be robust, therefore it had to be a very simple design. And I think that given that we are now out and we have shipped it out as product and we don't see that many bugs coming in for V8, that sort of succeeded. So you're claiming that Firefox is... You asked? Okay. That's the end of my talk.
In your example there, when you created a point twice.
Yes.
Your early example. When you create that point the second time, why don't you go ahead and know that you can create class 2? Say you create class 0 and then you promote it to 1 and then 2. Can't you just go ahead and remember this is going to become class 2, create that, and then you don't promote it?
Oh yeah, that's part of the knob strategy. We don't do any optimization in the compiler, so when you generate code for the first instruction, we don't save any of that for when we generate code for the next instruction. We don't keep information around, so we just say, oh, we don't know anything. So it's clear that in this case here you can easily optimize, so the transition going from class 0 to class 2 could be done immediately. So that was easy to do, but we haven't done that. Again, for us it was very important to get it out as robust as possible and make it available in open source format so people can see how we've done it. And the key here is that when you do VMs, you have to do a good runtime system. And then afterwards, you can always add like the regular expression stuff and a good compiler and stuff like that on top of that. It's very hard to do it the other way around. So if you start building a virtual machine and you start building the compiler, then it's often a problem because then it's very hard to fit the runtime system on top of a compiler. So that's it. Any other questions? Yeah.
Python is looking at using LLVM.
Okay.
Are you looking at that?
No. So I said before that when you generate code, it's generated into the object heap. So code objects are floating around in the heap like any other object. That also means that return addresses on the execution stack will be updated when you move code around. When you do that, you have full control over all allocated memory in the system. And it also means that when you do a GC, often you have to scan the code because inside the code you have pointers to objects. So all this relocation information that's needed for moving them or for tracing pointers inside the code is much easier when you handle it yourself. Okay, and it's building something that generates assembly code and put it in the heap is not complicated. Just take a thick book and go through it. Anyways, is that it? Thank you for being patient.